And we are going to be looking at this concept called qualitative analysis. And what qualitative analysis is determining which ions are present. So if I give you a beaker and it just looks like water, there might be things in it, yes? And you don't know what they are, so you need to figure it out. And that's what we do in qualitative analysis. One of the methods that we use is called selective precipitation, where we precipitate ions out one at a time. There are other methods that we use as well. What's up, Sean? There are other methods that we use as well. There's flame tests. I don't know if you guys have seen those in your earlier grades where, you know, you've got like a little bit of solution. If sodium, for example, burns orange, strontium burns red. Okay, so if you haven't had a chance to see that, maybe towards the end of the year, we'll take a look at that, okay? We're just gonna jump in with an example though. We have a beaker that contains either calcium nitrate or lead nitrate or both. And that means that in our beaker, we either have Ca2+ ions or we have Pb 2+ ions, or perhaps we have both. So we're going to outline a procedure that you could use to determine which of those ions are present. And this is where the selective precipitation comes in. We're going to precipitate the ions out one at a time. So the first thing you're going to do is you're going to look at page 4 of your data booklet. If you do not have a data booklet, please come and get one, okay? You are going to find something that precipitates calcium or lead, but not both. So find something that precipitates one of them, but not the other. We want something that'll precipitate either calcium or lead. You got long arms? Yeah, you do. Good. So check with your partner and see if you got the same answer as they did. Anyone have any suggestions for me? Perry. You could choose chloride, bromide, or iodide. Which of those which ion would precipitate with those? Is it going to be the calcium or is it going to be the lead? And why is this pen all of a sudden not working for me? That's okay. I have backup pens. So that's going to be our lead, because lead, remember, is low solubility. And what does that mean? Its state will be solid. So if I have a solution that contains lead and a solution that contains iodide or bromide or chloride, I pour them together, I'm going to get a solid forming. Is there another choice? Did anyone find another one, Joanna? Sulfur. So sulfide ion, yes, because sulfide, you'll notice that calcium is in the soluble category. Lead is not, so lead would be down here. So of our choices, let's go back, we'll write those down. Our options are chloride, bromide, iodide, or sulfide. We don't want to use all of them. We need to pick one. And I'm gonna pick chloride because it's probably the most common ion and it's really easily available, okay? But you could choose any one you want to. Let's pick chloride. This step you can call pick. So pick an ion that precipitates only one of the two. Before you do anything with it though, could you go into the back room and find a jar that contains only chloride ions? Does that seem likely? What's wrong with this picture? Yeah, but the lead is in the, remember the lead is in the beaker. Negative and negative do not attract. In fact, negative and negative, what do? They repel. So if nature would never let you have this in the first place, but if you did somehow manage to isolate all these chlorines and cram them together into a small space, what do you think would happen? It would explode, boom, like it would be a big, big explosion, because that's a very unstable state with those negative ions pushed up against each other. So that's a big old no. So we need to choose an ion to partner So we need to pick an ion and then we need to pick a partner. And if we're looking at chloride, bromide, iodide, and sulfide, those are all what type of ions? Those are all anions, which remember what's an anion? An anion is a negative ion. So if I'm going to pick a partner for my anion, the partner has to be a cation, okay? Yes. Because you know that sodium chloride is table salt and that's just around everywhere. Yeah, but when I say it's readily available, would I have a problem if you were doing this and you chose bromide? No, that's fine. Okay, you could choose sulfide, iodide, whatever you want to. Okay? If you were doing it in practical circumstances, you might be like, chloride is cheap, right? It's more expensive to go out and buy, you know, an iodide salt than it is to buy a chloride salt. So those are the sorts of things you would consider if you were doing it for real. But on paper, you can choose the most expensive ions you want. You want to use silver ions? Does it matter that a bottle of silver nitrate costs $300? No, it doesn't. I know, right? There's a reason we are not doing the silver titration for the whole class. I might do a quick demo of it, but there's a reason we can't all do it for all my 3 blocks. I'm like, yeah, that's a really expensive one. Anywho, the partner for an anion must be a cation, and you want the cation to be soluble with everything. because you're going to be mucking about with other ions later on. If you pick an ion that's soluble with chloride but would precipitate with something else, you might have problems later on in the process, okay? You also want a cation that won't react with anything else. You don't want to pick things that are acids, for example. So let's take a look at our data booklet and see if we can pick a cation to pair up with chloride. So what cations are soluble with everything? Your alkali metals are soluble with everything. Alkali metals are soluble with everything. Are there any other choices? Hydrogen. The problem with hydrogen is that hydrogen, what kind of compounds have hydrogen in them? Acid. So if you have anything that reacts with an acid, that's going to cause you problems. Yeah? We don't want to choose hydrogen because then we might have side reactions happening that we don't want. And you guys don't know this yet, but ammonium, the ammonium ion is actually also an acid. And so you could also get reactions with that. So we're going to stick with the alkali metals because they're not acids or anything like that. If you had to pick the most common alkali metal, what would you choose? Sodium. So we are going to say, to make your life simple, just always pick sodium as the partner. Yeah? Always pick sodium. Would it be wrong if you picked potassium instead? No. But I know that, like, if I give you too many choices, sometimes that becomes a little overwhelming. Yes? Then you have to remember more than one thing. If you just remember always pick sodium, then you don't have to think too hard. The nice thing is later, when we have to choose an anion to pair up cations with, we're going to choose nitrate. And nitrate and sodium, Na, both begin with N. So we're going to be like, oh, we can help, that'll help remember. Yes? But in the meantime, we're going to go here again. So we're going to pick something that's soluble with everything, unreactive with other substances. So that's going to be an alkali ion. Not NH4 or H because they are acids. And specifically, the best option is going to be Na+, because then you don't have to think very hard. But if you write lithium, that's fine. If you write cesium, that's fine. It's a little bit of a weird choice. You know, rubidium is radioactive. But if you chose it, it would be correct, you know. But yeah, just stick with sodium and everything will be good. In our third step, we're going to ask ourselves, how much of this compound, what's the compound we have now? We have sodium paired up with chloride. How much of this compound, sodium chloride, do we need to add? In our beaker, we have some lead, possibly. I'm just going to write this assuming I have lead and assuming I have calcium, yes? If I was to add 2 chloride ions, how many of my leads would that precipitate? It would precipitate 1 because these 2 chlorides would get together with that 1 lead and I would get a precipitate. Now, what if I decide in my next step, now I want to check to see if calcium will precipitate. And maybe I decide to add something that precipitates calcium. But let me tell you, everything that precipitates calcium also precipitates lead. Everything. You cannot precipitate calcium without precipitating lead. So if we only add 2 chlorides, and I need more than that to get rid of all the lead, now let's say I'm adding, the next anion, what's going to happen? I'm going to see a precipitate even if I don't have calcium because the lead will precipitate. Does that make sense? Right? So if I now add, sulfate. Let's say I add sulfate. And let's say I didn't have any calcium. But I'm checking for calcium by adding sulfate. The lead will get together with the sulfate, and I'll see a precipitate and I'll think, oh, I've got calcium. But really I don't because I just didn't manage to get rid of all the lead. You're not going to have to explain that. But what it means is that when you add your chloride ion, you want it to get rid of all the lead. You need all the lead gone. Fortunately, we are not doing this in a quantitative fashion. You don't have to give me any numbers. You just need to say that you need to add an excess, which means more than is needed, to react all the lead. Of the NaCl. You could also write how much to add. I add more than is needed to react all the lead, but that's really long and excess is nice and short. Yes? So in step 3, we need to make sure we add an excess of our compound. What was step 1 again? We're trying to decide, is calcium here or is lead here or is it both? So first we have to pick an ion. What does that ion have to do? It has to precipitate one of them, but not both. Then what do we have to do after we pick our ion that precipitates one, but not both? Pick a partner for it. Who's the partner going to be if you need a cation? Na, okay, sodium. How much, step 3, how much of that sodium chloride are you going to add? An excess, okay, so now we're on step 3. So now we've added an excess. Now back over in our beaker, we maybe have some calcium, but floating around in here, we already have some lead chloride. Yes? Ooh, before we do that, we need to make a statement. I forgot about that. Step 4, make a statement. If you got a precipitate with the chloride, there was lead. If there was no precipitate, there was no lead. Okay? So step number 4 is just make that statement. There's 2 if statements. If there is a precipitate, if there is no precipitate, and you just say what you figured out from that. Okay? Now, back to our beaker. What does it look like when we have a solid floating around in a solution? It looks cloudy, okay? So this looks cloudy. If we did have lead, it looks cloudy. Now let's say we add something to precipitate the calcium. So these two guys get together and they form a new precipitate. Well, how could you tell if it's cloudy from the new precipitate or if it's cloudy from the lead chloride? Is that a problem? It looks cloudy, and you add some more stuff, and oh, it still looks cloudy. Yes? So that's a problem. So what could we do to fix that problem before we start adding something to precipitate out the calcium? Okay. We can remove the precipitate. See if you can think back to grade 9, 10, 11, you might have talked about it, some way that you could separate a solid that's floating in a liquid. See if you can think of something that you've done. Joanna? You could filter it, yes? Okay, filtering is an excellent way to separate the solid from the liquid. So let's just fill this in here. We now know if lead was present, we can now add something that will precipitate the calcium. But wait, our solution is cloudy with the lead chloride. How can we tell if another precipitate has formed? Well, we need to remove the PbCl2 precipitate from the solution. And we can do that. One example of way to do that is by filtering. And that's actually on your next page. It's the second method. Okay, so filtering. If you're not, how many people have filtered something in the past? Lots, anything. Most of you have filtered something, right? Yeah. Whether it be in chemistry class or just in your normal life, right? Even if you make coffee, you're filtering something, right? All that lovely coffee taste comes through and you don't have all those grounds. Yeah. So this is just showing what would happen if you have your suspension of a solid in water. Okay, it's called a suspension when you have a solid hanging in the water. It is suspended in the water. We pour it through, and all the little solid bits are too big to fit through the pores in the filter paper. So the filter paper has tiny pores in it. Water molecules and ions are small enough to fit through those pores. The solid particles are too big to fit through the pores. That'll be, yeah, at the top. It's very, yeah, they'll do it to spin out blood. They use it for all kinds of things, yeah. And we'll talk about that one in a minute after we've done the solid is too big to fit through the pores. I'm sorry for my terrible spelling, but I'm just trying to fit it all in. Enough and through. Now, if you are not planning on taking a chemistry lab course in your post-secondary, you do not need to know that the clear liquid that comes through is called the filtrate. But if you are taking one, it's not a bad thing to at least have heard the word before. Okay, you don't really need to know it for this year, but for a lab course you would. So that clear liquid is now the filtrate. It would contain the sodium ions, which were spectator ions. It would contain any of the extra chloride ions. It would contain, if we have calcium, it would contain the calcium ions. But the lead chloride is left behind. And this solid residue here, it's called the residue. Again, don't need that for this year, but if you're taking a lab science in post-secondary, you might want to know that that's the residue. That's one way of doing it. And if you're writing about separating ions, that's a nice way to choose, because filter, all you do is you say, oh, filter out the precipitate. That's short, yes? Anyone do a filtration in Chem 11? How long did it take? So long, like watching paint dry, yes? Drip, 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 right? Like not particularly fun and exciting. So there is another way of separating a solid from a liquid that is faster, okay? It involves some bigger words. So if you're writing it, filter's fine. But you might also want to know that you can centrifuge and decant. So centrifuging, we get a centrifuge. Are you guys familiar? Does anyone have a top-loading washer, like washing machine? Where do the clothes end up when that thing spins around? They end up at the sides, out at the sides. Or if you've been to like the PNE or one of those things where they have that thing that spins you around and you're on the wall, right? You get pushed out against the wall. With a centrifuge, everything spins around really fast. The things that are the most dense get pushed out the farthest, and the things that are least dense stay on top. So in your test tube that you put into the centrifuge, the solid, which is very dense, will go to the bottom. Okay, and the supernatant, which is what they call the liquid, it's not filtrate anymore because we didn't filter it, still contains the same stuff as the filtrate would, but they call it the supernatant. Again, do you need to know that word for this year? No. If you're taking a lab course, yes. So we have our test tube, and down at the bottom, all the solid has kind of collected together into a pellet, which is what we call it. And on the top is the leftover solution with the ions in it called the supernatant. Okay. And then, because we've separated them, but they're still in the same container, we need to get rid of the liquid somehow. And really, you could use a pipette and suck the liquid off, but most of the time we just do it by using this word, decanting. Has anyone ever heard the word decanting before? Yes? So, yeah, like they actually, there are wine decanters, because if you make wine by like the old-fashioned process, like not in the, the industrial process that they do it, there's a sediment at the bottom because the yeast dies and it falls to the bottom, and it'll settle out over time. And what they would do is they would take off and they would pour off the liquid and leave that solid behind. Yeah? We're going to do the same thing here. We're going to have the solid, which is going to stay behind. And we're going to pour the liquid off. And they didn't have any pictures of decanting from a test tube, so I was stuck with a picture of decanting from a beaker. But I think you guys can make the leap to imagining that coming out of a test tube. Okay. So now we've got this supernatant, or the filtrate, anyway, the solution without the solid in it. And now we want to decide, is calcium there? So I would now like you to go to page 4 of your data booklet and find an ion that will precipitate with the calcium. So who's one choice? Sulfate, because sulfate with calcium is low solubility, and low solubility means that it will form a solid, a precipitate. Now, sulfide is not a good choice because calcium is soluble. How about hydroxide? Could we use hydroxide? Yes, we could, because hydroxide is soluble with our alkali ions. Is calcium an alkali? No, calcium's an alkaline earth. It's in column number 2. The alkali ions are only column which? Number 1. So calcium is not up here, so calcium would fall down here, and it would be low solubility. So we have a couple of choices. We could choose sulfate or hydroxide, or could we choose phosphate, carbonate, or sulfate, or sulfite? Yes, because again, calcium is not an alkali. It's not hydrogen, it's not NH4, so calcium would fall in the all others, so it would be low solubility. So our choices. Sulfate, SO4, hydroxide, OH minus, carbonate, CO3, 2 minus, phosphate, PO4, 3 minus, and sulfite, SO3, 2 minus. You do not need to list them all. You just pick one, okay? We're only listing them all because we're learning, right? At this point, we're like, oh, I could pick this one, I could pick that one. I'm going to choose hydroxide just because but any of the others are also perfectly good, no problem. What do we do after we have picked an ion? After we pick an ion, we need to find it a partner. Yes, you pick an ion, you find it a partner. Who would you like to partner up with hydroxide? Sodium, yes, because you don't have to think. Sodium, okay. And that means we're going to have NaOH. What do we do with the NaOH? We just fling it around the room like confetti. What do we do with our NaOH? Add it to our solution. How much do we add? an excess, add an excess and once we've added it, what are we going to be looking for? We're going to be looking at our beaker to say, hey, what happened? What are my two choices for what happens? Either you get a precipitate or you get no precipitate. Yes? Did you guys ever watch Bear in the Big Blue House? No? Yeah. Anyway, so cute. They have this little, it's like a show for little kids. But, you know, they were doing opposites. That was the theme of the show that one day. And so they're like, you know, what's the opposite of open? And they're like, close. What's the opposite of up? Down. You know, they did a whole bunch of them. And they have the little kids answering, right? And someone says, what's the opposite of apples? And the little kid looks a little funny. He's like, no apples. It was so adorable. Anyway, so what's the opposite of precipitate? No precipitate. So we are going to say if a precipitate forms, what do we know? That Ca2+ is present. If no precipitate forms, no calcium was present. And then at this point, you could choose to just be done because that's your last ion. What if we had another ion that we needed to find? What would we have to do before we went on with that next one? We would have to remove our precipitate by either, what are the two things you can do to remove that precipitate? Centrifuge and decant or filter. Okay. So I think I wrote down everything that was here. Let's scribble out or K because I want it to just be Na. I want it to be simple, simple, simple. Pair up the hydroxide ion with sodium, add an excess, we've already written this, if you don't want to write it, it's fine, of the NaOH to ensure all the calcium is removed. Make a statement if precipitate forms, calcium is present, blah, 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 blah. Since there were no other cations, you can just finish here, but if there was another cation, you would remove the calcium precipitate by either centrifuging and decanting or filtering. We're going to do another example with anions. The anions are usually, maybe they're a little trickier, I don't know. So you need to find something that's, our last one had two cations that we had to separate. This time we need to see, do we have phosphate, do we have sulfate, or do we have both? First, you need to pick an ion that will precipitate one or the other, but not both. So go check on your data table, see if you can find one. Any possibilities? Sorry? Beryllium. Let's see, will beryllium work? Beryllium will precipitate with, yeah, beryllium is not here, right? There's no beryllium there. Beryllium would be up here. So that would be okay with the sulfate to not precipitate. And then beryllium would be down here. Here's a little hint. If you're working with anions and you're like, which one am I going to be able to precipitate out without the other one? It's always going to be one near the bottom because the ones near the bottom are the least soluble. So you'll find like I'm always going to be precipitating out the phosphate before the sulfate. Are there any other choices? Yes? Iron. Iron 3+, sure. Iron 2+ or 3+, right? Because iron is not one of those ones. I'm probably going to choose iron 3+ because iron 2 isn't very stable. But if you chose iron 2+, that would be fine. Any others? Yes? Magnesium. Yeah, magnesium. Any others? How about copper, nickel, chromium, vanadium? You know what? There's like tons of different options here, okay? So we're just going to pick one. Why don't we go with the beryllium since that's the one we did at the start, okay? So let's go with beryllium, but any of the other choices would be good as well. Now we need to choose an unreactive anion because in this case we have beryllium 2+, which is a cation, and you cannot go to the back room and get a bottle of cations on their own. Remember, cations are what kind of ions? Positive ions. And so our unreactive anion, can you go guys go find me an unreactive anion in our data booklet? An unreactive anion, something that does not precipitate with anything. Yes? Nitrate. Yes? You'll see acetate is also there, but acetate, although you don't know it yet, acetate is actually a weak base. So it could have some interactions that you are not aware of. Yes? So just like we're going to say always choose sodium, you are always going to choose nitrate. So you got Na if you need a cation, you got NO3- if you need an anion. So we need an unreactive anion to pair up with the beryllium. And the best choice is always nitrate. And what would we write in our next step? Add an excess of, and then we need to make a compound out of beryllium nitrate. What's the formula for beryllium nitrate? Be. Do we need anything else? We need 2 nitrates because we only have a 1 negative charge there. So we need 2 of them to bring it up to 2 negative to balance out the beryllium's 2 positive. Then we make our statements. if a precipitate forms, let's see, what were we precipitating with? The beryllium was precipitating with the phosphate. So if we get a precipitate, we know that phosphate was present. If we did not get a precipitate, then no phosphate was present. What do you need to do next? Tell your partner. Do something to separate them. Yeah, what are your choices? Filter out the precipitate, or what's our other choice? Centrifuge and decant. And if I'm really clever, either Friday or Monday, I'll actually pull out the centrifuge and get you guys to give it a try, okay? Because it's a fun experience, okay? Filtering, I mean, it's not fun, but it's kind of long and involved. Did I just leave more space? Oh yeah. After we have done that, what do we do next? We need to find an ion that will, a cation that will precipitate out the sulfate. So please do that. And you'll notice I've started numbering at 1 again, because it's kind of like I do 1, 2, 3, 4, and then maybe 5, and then I'll do 1, 2, 3, 4 again to get that ion out. Did you guys find an ion that would precipitate out sulfate? Thousands of choices, yes? Oh no, not thousands, only how many choices? 5. We could use which ones? Ag, Ca, strontium, barium, or lead. Which one would you guys like to choose today? Calcium. All right, let's do calcium. Okay. And I can't remember the last one, but that's okay. So we're going to pick this one. What do we do after we've picked our ion? Find its partner. Who would you like to partner up with calcium 2+? Nitrate. What do we write in step number 3? What do we add to the solution? An excess of CaNO3 to the solution. Now, you don't actually need to write anything down for step 1 and 2. You really just start writing in step 3. Yeah? In step 3, you need to write something. In step 4, you need to write something. What are we writing in step 4? If a precipitate forms, and I think what were we looking for? We were looking for sulfate, SO4 2- is present. If no precipitate, no SO4 2- present. And then you're done. Woohoo! So we have about, I don't know, just over 10 minutes left. And you guys could do some of those practice problems, okay? In question number 2, the questions actually get a little simpler because they just want you to separate out ions that you know are there. So you don't have to write that step. If a precipitate form such and such was present, because you know that it's present, you're just trying to get it out individually. So you're separating out the lead and then the calcium, okay? If you get confused by it, let me know, but I don't want to stand and talk about it because you've listened to me talk a lot. Yeah? Hi. Yeah. So your homework will be that worksheet. You're welcome. Yeah, we'll see. If it doesn't, I'll woohoo! Nice. And just checking, does anyone else have a lab that they haven't handed in yet? Okay. And I need to find that number 2 and 6.
It's lunchtime, it's lunchtime. Happy, 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 it's lunchtime. I'm especially happy today because tomorrow's day off. So, yeah. So it's lunchtime. I get to eat my lunch today. Yesterday I didn't get to eat a lunch. Remembrance Day assembly is during block 3 at the beginning of the block. Hi. Oh, sorry? Of course you can. There you go. Looks good. Excellent. Omar Abdulhali, Paul Arturo, Abdullah Ahmad, Valera Alvarez, Gavin Bernie. Please come to the office to pick up your gold card. Justin Yi, please come to the office. Justin Yi, please come to the office.
understand.
I have go-karts at the office for Karina Chen, Joshua Choi, Daniel Cooper. If you would like your go-kart, please come to the office.